Okay. Okay, let's see. We have let's record. Let's take a look at what we have from the last class. From the last class, we have already learned the fixed point methods, and then let's see what is the fixed point methods. Fixed point method, you are using the fixed point methods to solve fixed point problem. And let's see, this one should be your notes here. Okay, so this is the some numerical methods we learn to solve linear equation. We have already learned two methods. One is the bisection method, which means that you just divide the interval into two parts and you get the middle point and then compare the values at all these the endpoints and the middle points and then get the opposite side and then let it to be the new intervals, new interval to find the root of the problem. And this is the bisection method. And for the fixed point method, and we define a new problem, and then that's the fixed point problem, and then that is just GP equals to P. And for the fixed point method, we just use the G functions to generate a sequence of number. Let me see. So for the theorem 2.3, it just shows you the existence and uniqueness of the fixed point for the G function. And this is the existence and uniqueness. And for the 2.4, it's telling you that the algorithms actually converge with some assumptions on the G function. The G function assumption here is the same as the one we have for the theorem 2.3. And but here we have the generation through for the sequence here, the Pn sequence. We generate this Pn sequence with Pn equals to Gpn minus 1. And with the assumptions on the G, this sequence converges to a unique fixed point P. And this is the theorem 2.4. And I believe I have shown you the proof here. And we also go to the corollary and then say something about the convergence rate of the fixed point method. And today, we are going to talk about the let me see. We are going to talk about a new methods, and then that is the Newton's methods. You have met Newton's several times in the mathematics class, and then Newton's is so important. And actually, once again, we are going to learn some things that is related to Newton's. I think it's not the right. I think this one is not invented by the Newtons, but it's something related to or show some respect to Newtons. So here, let's see the Newton's method. And for this one, the Newton's methods, it's used to find the root. This is the methods to find the root of the function fx equals to 0, this equation. And this is something different from the fixed point methods. The fixed point methods, and then you need to translate the root finding problem to the fixed point problem. But this one is directly used to find the root of the equations, the linear root finding problem here. And so I have some assumptions on the function f, and So the fx is the, suppose the fx is in the C2, which means that the f is continuous and the derivative, the first derivative is also continuous, and the second derivative is also continuous. And now let us, so we are going to divide this method. Let me write this down. This is the derivation of this method. The mathematical background before the mathematical derivations before behind this Newton's methods, and this is the derivation part. So it's we can use the Taylor expansions to derive these parts, and I'm going to suppose this part the function is in the C2, and let the p zeros to be in the interval a and b. And let's say this p0 is an approximation to the p. So here the p here is the solution at p equals 0, and then that means that it means that the p is the root of the equation, and we are saying that the p0 is the initial guess to approximate that p. And now we have one assumption on this initial guess, that is the difference between the true solution and then the initial guess is small or small enough. And you will see how small it is later on. And let's consider the Taylor expansions of the fx function about the point p0. Evaluate at the let's the x to be p. And so which means that if we do the Taylor expansions here, and then you will see this happens. So on the left hand side, I have fp, and then I'm going to expand the Taylor, do the Taylor expansions around the point p0. And so I got p at p naught, and then the second term should be at prime p naught, and then p minus p naught. And I'm going to do it with the Lagrange remainder. And the Lagrange remainder here, we have the f prime prime, that is the second derivative, and then the c, because the c is depending on the p, and then so I just write down the dependence here, c_p, and divided by 2 factorial, and then that's just 2, because 2 factorial is just 2 times 1, and p minus p0, and then to the 2 order. And this is the Taylor expansions, and then where the CP is in between these 2 points. It could be p0 p, but it depends on the order of p and p0. So this is just between the p and p0. And now, because the p is the solution, the p is the solutions to the equation over there, the fx equals 0. And so p equals 0, and let's see. So since p equals to 0, which means that the left-hand side is the 0. So this equations gives us, on the left-hand side is 0. And on the right-hand side, we keep the things on the left-hand side. And there's one more term here. And as we just said, the P0 is close to the P solution, the solution P enough. And we just mentioned here, we have assumed that P minus P0, so the difference between them are small enough. Sorry, excuse me. And so we are going to ignore the higher order term here. So which means that we are going to ignore this term. Ignore this second order term here because we assume that the P minus P0 is small enough. And then compared to this part, and then this is our highest order term, and then this value is let's say, because this is assumption here, and then this part is much smaller than this part because we have a second order here. And because this is because the because I'm going to use another color to write down the remark here, because the P minus P0 is more. And then because this, and this one, the P minus P0 is much smaller than the two other terms. It's smaller, not just smaller, it's much smaller because it can be another magnitude. Let's say if the P minus P0 is like equals to 0.1, and then the first item is with the magnitude 0.1, and then but the second term here, this second order term here is with the magnitude 0.1 to the square, and that is 0.001. It's just 0.01. So the magnitude here, we expect this terms with much smaller magnitude. So we are going to write down the approximations in this way. The 0 is approximately equals to at P0, at prime P0, and then P minus P0. And this means that, so I'm going to, this is approximately equals to 0. And let's solve for the P, and we got so if we solve for P, and then we get this one should be the P equals to, is approximately equals to P0, and then minus F P0, and then F prime P0. And this is the things. So if you take a look at here, the derivations, we just get the Taylor expressions around the solution, and then just take away the second order term because it's much smaller. Then we get the approximation here. It's approximately equals to 0, and then we solve for the P. And then the P, the true solution, is approximately equals to the initial gas and the minus such as things here. But actually, in the Newton's methods, we use this to be our next approximations to the P, and that is the P1. And once again, you get this P1 into this things that in here, the expansions here, the Taylor expansion here, and then this one is just P1, P1, and then P minus P0, P minus P1, and all those things here will give you next iteration, and then that is the P is approximated by the P1 minus P1 and divided by F prime evaluated at the P1. And this is the Newton's methods. And this is the equation or the generation through to get the next iterations result. And all the things here you can see it's just about the Taylor expansion and skipping the higher order term here. And so this is the Newton's method. Let me just conclude here. So the Newton's method. So this is the Newton's method. So starting with the initial gas, and then as you can see at the very beginning, initial approximation. We start with the initial approximations P0, and which is close to the true solution P, and we generate the sequence with the following rules. And you could say this is something similar to the fixed point mappers, but here we are using another rule or the functions to generate the next number. This is the Pn, and then it's equals to Pn minus 1, and then minus the f functions evaluated at n minus 1 point, and then the divided by the derivative. And you would quickly figure out that there's one disadvantage for this Newton's methods, because we have the denominator here, that is the derivative, right? And if the derivative evaluated at some point is 0, and then our method just stop. So this is one disadvantage here, and then I will fix this with another method later on. But let's say, okay, this function works perfectly, and because we have some assumptions of for the function here. Oh, I forgot to write down this assumption. This is so important. For the Newton's methods, we also assume that the apply evaluate at. So let me just insert somewhere. So let's say I'm going to insert all these things in between here. So there's another assumption. Apply P0 does not equal 0, 0. And this is because, as you can see here, we cannot have the sense equals 0, 0 here. But although the initial point, the first derivative divided at the initial point does not equal 0, but it does not guarantee the first derivative divided at the later items in the sequence does not equal 0. So this method has a very big disadvantage, and but people have a lot of variations of this Newton's method, and it could help you to get a faster conversion sometimes, and maybe sometimes it could help you to avoid such an first derivative evaluated at some points equals to 0. And this is the things, but I believe that if the initial point is close enough, and then if we have the f function is in the C2, and then if we do the iteration, and then sometimes we can avoid the first derivative that is equal to 0. That is because the f function is in the C2 space, and we can choose. But this method, it depends on how you choose the initial points. So this method has its own disadvantage. And let's see. The next things, I'm going to give you one picture to take a look at the how this Newton's method works. So this is the picture, and we are starting from here. And this is the function f equals to fx. And we are going to start from here. This is our initial guess. So I'm going to just divide something first because it's hard to see why this is the intersections for here. So I'm going to write down the function here. And let's say the function, this equation, this line. So this line, what's this line? This black line here is the function with the derivative apply p0. This is the secant, the tangent line of this function f. So this is the tangent line at the point at the point p0 at p0, and if you use the point slope form, and then you would get this function is just the x minus p0, and then y, and then plus the at p0, and this is the slope point form for this tangent line. And let's see what is the intersections at the x. So the intersections intercept the interception point, the x-intercept is just C. We solve for let the y to be 0, and then it equals to the f prime p0 x minus p0 plus p0. And let's solve for the x, and we get this. We get the these things equals to, it's actually equals to p0 and then minus at p0 and then at prime p0. And as you can see here, we can compare this. This is the x-intercept, and then we can compare this to the formulas we have there. And you will immediately find out that this x-intercept is just the numbers, the p1 number in the sequence. This is the p1. So which means that in this picture, we draw, this is the function f, and then we draw the tangent line at the initials point here, and the x-intercept of this tangent line is just the next numbers in the iterations in the sequence. And now I just go to back to the function again, and then this is my p1 at p1, and again I get the tangent line of the function here, and then I got the x-intercept for this tangent line, and then this is x-intercept is just a p2 in the sequence. And the next time you are going to find out the corresponding points on the function f. That is the p2 at p2, and then you do the tangent line again, and then you will see this is the tangent line, and then it's gradually approximating to the root of the function, and this is the root of the function p at p equals to 0. And you can see this idea is just draw the tangent line, find the intercept, draw the tangent line, and then find the intercept, and then again, here is approximating to the p, the root p. And any question about the intuitive idea of the Newton's methods? Any questions here? Tangent line, intercept, tangent line, intercept. And then this is the idea of the Newton's methods. And I'm going to show you the Newton's methods here, the algorithm. And I will also include the stopping criterion here. Maybe we will have a coding question about this one. But you already get one small coding questions in your homework 5, but that one is super easy because I have given you the reference, and you just need to take a look at the reference code. And for this Newton's methods, if you take a look at the pseudocode, it is not used a lot of time when you take a look at pseudocode, and there's some difference between the idea we have. We have a sequence of Pn, but in this pseudocodes, we just need to use 2 points to get the algorithm work. So here we just use a P and P0 here to help us to update the number, and each time you can see this is a step 4, and this step 4 is to take a look whether we get close enough to the solution, and this is just if you take a look at the sequence here, and then this actually means that because for this pseudocode, and then we just use the P and P series to store the numbers in the sequence. And then this one is actually means that the Pn minus 1 minus the Pn is smaller than the tolerance you decide. And this is the pseudocode, and this is the actual algorithm, actual numbers we have in the sequence. And but here you just need 2 numbers throughout the iterations, and that is just the Pn minus 1 and the Pn. And actually here the P, let me see, the P0 here is corresponding to the Pn minus 1, and then the P here is corresponding to the current iterations number Pn. Does that make sense? So actually this P0 in this pseudo algorithm is corresponding to the Pn minus 1. And then the P is corresponding to the Pn here. Any questions? It's just like updating these 2 numbers. So let's see, P1, P2, P3, P4. And then for each iteration, we just have, for the first one, this is the P0. This is the P0s in this iteration, and this is the P in the first iteration. And then for the next iteration, your P0 is changing to this one. And then this is the second iteration P. And this is how the things works. And then you don't need P storage places here to storage n numbers. And then you just need 2 places to help you to finish this iteration and then get the satisfied results to approximate the solution P. And once again, we have some stopping criteria here, and you can use the difference between 2 iterations number and or the relative error between the 2 iterations number, or you can evaluate at the f functions at the Pn, and then if this value is small enough, and then we can stop the iteration. And this is the stopping criterion. Let's see the next. I'm going to give you 1 example on this one. Okay. And let's see. Maybe I should go back to here. So this Newton's method, it gives you a fast convergence result and to get the solutions of the F. And if you go back, let's go back to what we have for the, let me say, it should be the fixed point methods. So let's see, there's some things we need to go to take a look at the fixed point methods. And actually, do you see something magical here? This is the example we show in the iteration, the fixed point methods. And we write down some equivalent formats to the root finding problem. And then this is the fixed point methods, right? And let's see the E format. If you take a look at the E format, you will see this. This is actually the X. So this is the root finding problem. Fx equals to x cubic plus 4 fx equals to x cubic plus the 4x squared and then minus 10. And if you take a look at the format here, it's actually dx and then minus fx. And this one is just the f prime x. If you take a look at the f prime x, it's just equals to the 3x squared and then plus ax. And this is the derivative of the derivative of the fx. And this is actually what is this? This is the Newton's methods format. You have your Pn minus 1 and Fpn minus 1 and F prime Pn minus 1 here. And actually here is just the g. You set the g function here and then the g function gpn minus 1 and then it equals to pn minus 1 and then fpn minus 1 and then f prime pn minus 1. And you let this one to your pn. This is actually the Newton's methods. And if you take a look at here and then compare to what you have for the other example, you will find out that this Newton's methods works very well. And you have only 4 iterations to get the desired result, the desired accuracy. And so this is the examples, and then let's get back to the another example. And let's see, this is the example here. So I'm just going to copy and paste. This one, you don't need to, let's see, let me just write down the example here. Examples, and then let's find the root fx and then cosine x and then minus x equals to 0. And we are going to approximate this things with 2 methods. And then the first method is the fixed point methods. And then the second one is the Newton's methods. And as you can see, if we want to translate this one to the fixed point methods, is so easy to see. We can set the g to be cosine x. So for the first one, and then it's actually we can do a transformation for the function, and then we let it to be x equals to cosine x. And now we get the g function is equals to the cosine x here. And this is the fixed point methods iteration. And which means that we are going to generate the sequence by gpn minus 1 and then pn. This is the fixed point methods. And then for the Newton's methods, we are going to generate the things by, so the Pn equals to, let's see, it's a Pn minus 1. And what is the Fx? Fx is just a cosine Pn minus 1. And then minus the Pn minus 1. And then divided by, and we have the negative sine Pn minus 1 and then minus P minus 1. And this is the iteration, how we generate the sequence of number in the Newton's method. This is the Newton's method. And then this is the fixed point method. And then for the fixed point methods, it's actually finding the intersection point of the x and the cosine x function. And now we are going to give you the result here. And what's the true solution here? The true solution here is should be around 736 something. And this is the table. And let me see, do we have the value for the true solution? Actually, this one should be around this number 0.7139 something. Okay, good. This is the table, and you will see actually the true solution here. I should give out the true solution for this one, but let's see. So it's just stop the equation here for the Newton's method, and then because this number is close to the we have the stopping criterion in these two methods, and then it stop once it gets to the previous one, and the difference between the previous one and the current one is small enough, right? And then we stop here, and then we view this one as the true solution, the approximations of the true solution. And but here, if you take a look at the fixed form method, this one is the fixed form method. And then you will see actually the difference between two iterations is very big. And it is around at 0.007 here. And then we accept that, and then we stop here. But actually, you will find out that the Newton's method is very powerful. We can stop the iterations just here with 4 iterations. But for the fixed form method, you have like several iterations, and that it's not getting even better, a good solution of a good, even not as good as we have in the Newton's methods with this 4 iteration. And then you can see this is 0.736, and then I believe this one is more accurate than this one. And so this is a very powerful choose to find the solution of the f function. And I'll just show you the result here to take a look at how powerful is the Newton's method. And the next, we are going to take a look at the convergence result. But I want to remind you of that. If you double check this, that keep around this point, and then you will see that the derivative is not close to 0. And this is why we have this method is so powerful for this one, and because it's not close to 0, the derivative, and this is why, and the Newton's methods usually works better when we have derivatives around that point is not close to 0. And so now I'm going to give you the convergence results about the Newton's methods. And as you can see at the very beginning, and then we have several assumptions. And then let's see, we have the assumption, the P, the initial guess is close to the true solutions enough. And we also assume that the derivative here does not equal 0. And actually, we have such an assumptions in the convergence result. The convergence result here, I want to mention. Let me just move this part to the. Let us save some space here. Okay, so I'm going to talk about the theorem, the convergence result, but I'm not going to prove this today. I'm going to leave the proof to Friday. And convergence results of the Newton's methods. And if you go back home and take a look at this proof, and then it's very lengthy, but one part you might find very useful is to use to prove the exercise homework 3B in your homework. And then there's one part very useful if you want to get that homework done. And then this is the theorem 2.6. And then it would tell you when we will have the convergence results. So first, we still have the assumptions on the f function is C2 on the interval a and b. And if this is the solution, and then if the solutions is in between, is the solution of the fx equals 0. And we also have the assumptions at the derivative, and then it's the slot equals to 0. And this is all the assumptions on the f. F is C2, the continuity here. And then we assume that this is the root, and then the derivative around the root, the derivative at the root, that's not equal to 0. And then this is all the assumption, just the C2, and the derivative does not equal to 0. And then there is this. So there's one more thing about the initial guess. There's this delta which is positive, such that with the initial guess, with any initial guess, there is this delta bigger than 0, and then with any initial guess p0, and then it's in between this interval. It's around, which means that it's around the true solution, is close enough to the true solutions, such that the Newton's methods generate a sequence Pn, and this sequence is converging to the solution. The solutions P. And you will see there are 3 very important components here. So first, we assume that the f is C2, and then the derivative does not equal 0 at the root. And then there's another very important things in this theorems. The initial guess should be close enough to the p, and then we can have this sequence generated by the Newton's method is converging to p. And this is the 3 main components in this Newton's method. Any questions by so far? I'm not going to give you the proof today, but I would leave the proof on Friday, but you will find something very useful to do your homework in the proof. And the next, I'm going to use 3 minutes to solve the problems, the f prime derivatives equals to 0. So if this one, if in the sequence, and then sometimes, and then the f prime equals 0, and then how can we solve that? And there's one thing to make up this. So it's quite similar to what you have in the 104B. We are going to use some approximation here instead of the f prime itself. So I'm going to copy them. So let's see. So instead here, this is the Newton's method. Pn equals to Pn minus 1 and the minus f Pn minus 1, and then divided f prime Pn minus 1. But the problem is that when the f prime equals 0, and then our method just doesn't work. So what should we do with them, with these items? So people come with one method is something similar to the finite difference methods to approximate this value, this derivative here, and then which means that we are going to approximate this derivative at the Pn minus 1 with the So we are going to get not backward on the x-axis, just backward in the sequence, and then Pn minus 1 here, and then divided by the Pn minus 2 minus Pn minus 1. And this is how we solve this problem. So let's see. If we use this formula to approximate this derivative here, and then we can avoid the problems where the derivative equals 0. Because if we have the derivative or the denominator equals 0 here, we have already stopped our iterations. We already stopped the iteration because see, the Pn minus 2 equals to the Pn minus 1, and then we stop there. So this is how we avoid the derivative equals to 0 problem here, the issue here. We use these things inside here for this blue part. And this is called sequence methods. This is the sequence methods. And this is how we avoid the first derivative equals 0 in the Newton methods. And this is all the things I want to mention today. And next time I will give you an intuitive look at the sequence method, and also the very important things is the proof of the theorem of the Newton's methods here. And that's all the things about this week, and also the Friday, the things on the Friday. And that's all. If you have any question, and then you can come over here. But I want to remind you of something here. If you have the f prime does not equal 0 around this point, and then you should definitely use the Newton's method. The Newton's method is better than the sequence method if you have better assumptions at the f prime. Newton's method is better, but the sequence methods can solve the derivative equals to 0 problem. Use the finite difference methods.
So this part is to use this and put it here to avoid
Yeah.
the 0.
Yeah.
What about, so this is the finite difference method?
Yes, it's a finite difference method, but it's kind of similar to the finite difference methods, but we're using the previous point.
Then where is the sequence method?